Chapter 1. What is STA and why we need STA? There is no strict definition about static timing analysis. It is a way to check if every path in the design can pass down the intended logic values in time when the chip is operating at a certain clock frequency. So basically all the timing problem is essentially check the path delay against some threshold, or limit to make sure the chip can operate at a certain speed. So here is the question, given a circuit consists of logic gates and the wires between them, how do you calculate the delay out of it? A traditional way is to flatten the design into transistor level, and do an SPICE simulation on it. There is no objection that SPICE simulation is the most accurate way to find out how much the delay is. However, we are talking about millions or trillions of transistors coexists in the same ASIC chips nowadays. SPICE simulation is simply too slow to compute such large amount of data. Or we can say the time cost for such task is unacceptable for production. Therefore, we truly need to have another way to find reasonably accurate delay results but with much faster turnaround time. So that is where STA comes into play. Let's see how STA address these two issues. The first task for STA is to maintain accuracy. We all know that a circuit consists of cell and wire. For cell, as long as STA can get accurate delay, it can maintain the accuracy. This can be done by characterizing the cell delay with SPICE into a library ahead of actual STA analysis. Once the library data is ready, STA can load in the cell delay value and get accurate results. For wire delay, STA can either estimate the delay before the actual layout is done, or extract parasitic first, and then calculate the delay after the layout is done. The second task for STA is to be fast. To achieve this, we have to reduce the amount of nodes that evolved in a timing problem. Instead of analyzing at transistor level, STA first convert the circuit into a timing graph in which each gate is the lowest level of delay elements. Also, the way to judge if the circuit can operate successfully is not simulation-based but is purely mathematical. This dramatically reduced the amount of time needed to handle a large design. Let's look at some more features of static timing analysis from its name. For a given timing path between a start point and an end point, the logic will never going to change once the chip is under analysis. So it is the same bunch of cells being exercised again and again every clock cycle. What STA does is it find this pattern and collapse the entire timeline of our world into one clock cycle and just analyze that one cycle. STA does this for all the timing paths on the chip at the same time. It then use a pure mathematical way to check path delay against timing requirement. This is why we call it static. The second feature of STA is, unlike SPICE simulation, it does not depend on input stimulus. Being a mathematic checking, it traverses all possible logic connections between any start point and end point, which in the end literally covers all possible scenario that may occur in a design. This feature sounds good but in some cases it impact the timing closure negatively. For example, STA will flag path that never used in real application. This could potentially cause over-design if people miss to filter that path out of analysis. This is what we called exhaustive. The third feature of STA is, it does not care about functionality. Yes, you have not heard wrong. How can such a powerful thing or not care about functionality? What if the design meet timing but have functional failure? Well, the STA is only responsible for making sure the path delay is within the target so that value from the launch point can be captured at the capture side without error. It doesn't really responsible for if the logic is implemented correctly. So in order to really be ready to ship your design to the customer, you have to run another type of check called functional equivalence check, where we assume the design meet timing unconditionally and then use some logic operation algorithm to check if its functionality has been correctly implemented. The last feature I will say about STA is it can be very conservative and pessimistic. How can a tool be emotionally pessimistic? Well, STA assumes everything is doing its worst when analyzing the chip. For example, it uses slowest delay a cell can get for max timing check. It checks the most restrictive pair of launch and capture clock edge. It has to do so because we need a robust design in all condition to consider into manufacture variation and application needs. So it has to have a lot of design margins or redundancy built in our design. As I said earlier, timing is the king of the backend design. 90% of the design cycle is to achieve timing closure. This can also be explained by looking at the role of STA in the backend design. If certain function need too many logic levels on the critical path, it is not possible to finish operation within one clock cycle at a given technology node. The RTL coding must be tweaked for easier timing closure so that the functionality can be physically implemented. Logic synthesis need to be optimized to reduce the logic levels and choose structure fast enough to operate at the target clock frequency. Place and route must do a lot of work to make sure the design can meet timing while being routable and can be manufactured. Even power integrity issues like IR drop need to take into consideration of the clock frequency, the timing window of signal arrival times and multi-signal simultaneous switching. This is why the STA engineer usually possess a core position in a backend team. The STA is such an important tool that any ASIC design can't be taped out without achieve timing closure. However, we should also know everything has its limitation, so does STA. The most obvious thing is, since STA is our safeguard in this ASIC design game, it has to be very conservative. It won't allow you to take any chance for failing timing and cause a functional failure. So that's why it considers so many delay variations and analysis modes only to try to make you meet timing even in most restrictive condition. Some of these restrictive condition can be purely mathematic combination or permutations, which are very rarely exist in reality, so if we rely on STA, we have to spend effort to close timing on the unrealistic case. Another point is, as mentioned earlier in this chapter, STA may flag paths that are not functionally meaningful to an application. We call such timing paths false path. Usually the architecture guys or RTL team will be the one to tell if a path truly meaningful in a design. So this is one of the items should be communicated between the RTL team and backend team. In the backend design side, we use SDC constraints to tell STA tool the paths are real or not. We will talk more about SDC in upcoming lectures. The last point is, it is not suitable for asynchronous design. In STA, in order to collapse the design timeline into minimal cycle, the launch clock edge and capture clock edge must have a deterministic relation so the pattern can repeat itself. If the timing path under analysis is between two asynchronous clocks, then the required time can be some arbitrary number. We can't rely on a static process to analyze it. That's why all large-scale designs are synchronous design. However, this doesn't mean there is absolutely no asynchronous path in the design. In some very predictable condition, we have special constraints to check timing for asynchronous paths as well. So let's learn the concept of operation condition. For any STA analysis, it really doesn't make any sense without talking about under what operation condition the analysis is done. The chip is working in a real physical world where the cell delay and wire delay values are largely impacted by its surroundings. A cell can be much faster on certain wafers than on some other wafers. A wire could be faster when temperature is high. Not everything is created equal, so we have to take all these into considerations. Thus, Operation condition is the first thing we need to notice of. Normally, the operation condition also referred as PVT corners. PVT stands for process, voltage, and temperature, which are the most dominant factors that impact the cell or wire delay. So first, let's talk about process variation. The source of process variation can come from a lot of places such as oxide thickness variation, voltage threshold variation, and channel length variation. The impact of process variation is throughout the entire STA analysis. It impacts the entire analysis from every aspect even though it does not directly factor into the mathematic equation of timing checks. There are two types of process variations, namely global process variation and the on-chip variation. The global variation is also called inter-die variation, which refers to the process effect that impact all device on the same die but differ from die to die. The on-chip process variation is also called local variation or intra-die variation, which refers to the variations in the process which can affect the devices differently even on the same die, so the same type of device placed next to each other could have different behavior on the same die. From Monte Carlo simulation between the impact of cell delay and process variation, the number of gates falls into certain delay range roughly follows Gaussian distribution. For the consideration of timing verification, which is normally tend to be conservative and pessimistic, we choose the nominal case as well as extreme corner case to guard band our design. So for the impact from global process variation, we end up having three corners, which is fast, typical and slow. Around the central line of each corner, the on-chip variation kicks in but with a much less standard deviation. There are largely two steps to make a CMOS device: transistor formation in base layer and metallization on higher layer. We already know that because of process variation, a single CMOS device will be either slow or fast or anywhere in between across different dies, which is described as a result of global variation. Thus transistor formation, where each gate consists of PMOS and NMOS, we have four extreme combinations in total. That is slowest NMOS and slowest PMOS, slowest NMOS and fastest PMOS, fastest NMOS and slowest PMOS, fastest NMOS and fastest PMOS. For metallization, we also have process variation due to manufacture parameters such as the thicknesses of the metal and the dielectric, and the metal etch, which affects the width and spacing of the metal trace in various metal layers. The extreme process corners are defined as the plus or minus 3 sigma corner from the nominal of process variation distribution, which models only the global process variation. The voltage and temperature corners are much easier to understand. Normally, the cell propagation gets slower as temperature goes up. But there is an important abnormal situation when we talking about temperature impact. Traditionally, the higher the temperature, the slower the cell delay. The cell delay can be roughly described by this equation, where μ is the electron mobility and VTH is the threshold voltage. As temperature increases, both the mobility and VTH decrease. Generally, the mobility has greater impact on the overall cell delay, so the cell becomes slower when temperature increases. But if the supply voltage is very low in some application, there is a range that VTH decrease overweigh the mobility decrease and the cell can get slower even if the temperature goes low. Normally, among all PVT corners, worst case slow and best case fast are the two need most attention, since they are the 3 sigma extreme corners and guard band the whole design. The slow process models correspond to the plus 3 sigma corner condition for the inter-die variations. The fast process models correspond to the minus 3 sigma corner condition for the inter-die variations. Voltage variation has a very simple relation: the higher the voltage, the faster the cell. Multi-voltage design which contains cells working at different operating conditions require libraries characterized for multiple voltages. To simplify multi-voltage analysis, the STA tool supports voltage and temperature scaling. This scaling allows us to analyze timing at voltage condition that is not being characterized. The STA tool uses interpolation to derive appropriate timing, noise, and power values to be used for current voltage condition. One-dimensional scaling only requires two set of libraries such that only one characterization parameter, voltage rail or temperature, is varying and remaining are held consistent across all libraries. Two-dimensional scaling needs at least three libraries to accommodate two parameter varying at the same time. Normally, to achieve good accuracy, if there are two libraries per dimension, in total we need 4 libraries to support the two-dimensional scaling. Three-dimensional scaling is not used too often due to it involves a lot of library characterization work to be done. It allows 3 independent parameters to be varying at the same time at the cost of much more library sample points. To start static timing analysis, we need to prepare some prerequisite inputs to the STA tool. First of all is the netlist which represents our design. STA only works on design that is already mapped into gate-level netlist. For pre-layout design phase, Verilog comes from logic synthesis tool or place and route tool before the design is detail rooted. For post-layout design phase, Verilog is generated by place and route tool after the design is detail rooted. Then we need timing constraint to make the STA analysis alive. The constraint is in the form of SDC, which stands for STA Design Constraints Format. For multi-mode multi-corner analysis, we need design constraints for each individual scenario. Then, after the design is rooted, we need to back annotate the wire resistance, capacitance, inductance value into the design. This is called the parasitic extraction. It is often generated from layout extraction tool and in a distributed RLC network format called Standard Parasitic Exchange Format or simply SPEF. Once we have the parasitic values, the STA engine can begin time the design by calculating delay through each timing arc. It will use SPICE simulated delay values stored in the timing model library. The timing model is in form of STA Liberty format or simply called DUDLib. Lastly, in case we want the STA to capture on-chip variation effect, we need to provide a table with deriving factors that should be used in calculation. The most often used OCV method nowadays is AOCV table. We will go over all these requirements in later chapters. Topic 1, Netlist. Netlist consists of cascaded nets and logic gates. The simplest case is a gate with single input and output followed by another gate like that. In this manner, these cells form into a chain. Such cells are usually buffers or inverters. In place and route tool, in order to fix timing or design rule violations such as max transition, max capacitance, PNR tool usually adds a lot buffers into the design. You will see such buffer chain or inverter chain along the path very often. A little more complicated case is where one cell drives multiple downstream cells. In such case, the output of a cell could fan out to multiple places. Multiple fanout is definitely okay and actually pretty common, but since it increases the load on the net, it could slow down the signal propagation. When the functionality needs to be implemented with more complex cells than buffer or inverter, we could have multiple fan-in cells in the design such as 2 input and gate, 3 inputs or gate and so on. Here, one cell is getting inputs from more than one source. This is perfectly fine and common also. The only thing need to watch out here is since multiple path is converging at this cell, it could result in a high utilized area for routing resources and may introduce congestion if many such cells are clustering together. However, If there are two different sources driving the same input leg of a cell, then it is a violation. If this happens, the two input sources is fighting each other, so the value on the net is no longer deterministic. This situation must be eliminated from the design. So the takeaway here is, for a net, it could have only one driver but multiple loads. For a cell, it could have multiple drivers and also multiple loads. Topic 2. Hierarchical versus leaf cell, net, or pin. We often heard two terminologies during discussion: the hierarchical pin, net, or cell, and the leaf pin, net or cell. They are both valid design objects and sometimes referring to the same physical entity, so what's the difference? Well, the hierarchical objects refer to the logic division boundary. It could be a pin or port on a virtual design wrapper. The leaf objects refer to the physical cell boundary, usually means a pin or port on a library cell. The leaf is the lowest hierarchy in a design. Topic 3. Immediate fan-in or fan-out. To a cell or net, the immediate fan-in refers to the leaf cell which is directly driving that cell or net. The immediate fan-out means the leaf cells driven by the particular cell directly. They are the first cells encountered when you trace the netlist upstream or downstream. The fan-in cone and fan-out cone of a cell is not limited to only the first encounter though, they are referring to all the cells could be traced backward and forward from where the cell locates. Topic 4. Basic query commands. Get cells or get pins or get nets are the most basic and frequently used commands to manipulating design objects. By default, the commands will only return objects in hierarchy of current design scope. For example, when I just do get cells *reg, it returns all the cells with reg in the end in current hierarchy. We can tell from size of collection command that we have 18 of such cells. The option hierarchical can be used to broaden the searching range of this command all the way from current hierarchy down to the leaf cell level. So with here option, the same command returns 22 design objects. Compared to previous result, ICAKE0/miss outstanding reg and if stage 0/red for valid reg now appears on the list. We can then narrow down the search result if needed by applying filter switch. Like what we did here, once we use outstanding as a keyword to refine the results, this command will return only ICAKE0/miss outstanding reg since no other cell names matching our criterion. If you know the full hierarchical name of a design object, you could directly use getCell or getNets command on it. GetPins command can be used to set scope on a particular pin, or to find all available pins on a certain cell if of object is used. Here, we have found all the pins of cell miss outstanding reg, including set or reset, data input pin D, clock pin CLK, scan related pins scan in, scan enable, output pin Q and QN. Since the cell doesn't have a dedicated scan out pin, most likely the Q pin is reused as scan out pin during scan mode. The getNet command can also be used to find out all available nets hooked up to the particular pin. Here we find the net connected to the clock pin of miss outstanding reg is named as ICAKE0/clock. One useful switch along with getNets is segments. It can return all the hierarchical name referring to the same nets. I mean the same net could have different names in different design scopes, so for ICAKE0/clock, it is being called net 184 in WB stage 0 hierarchy. If use top net of hierarchical group switch along with segment, the command will return the net name in top design. In our case, it's simply clock. Once we get the design object, sometimes we would like to know some attributes on it. Depending on what the design object is, their attribute could be different. We can use list attribute command to list out all the available attributes on the object. Class can be used to specify what kind of object it is, and application means only listing out attributes defined by the tool. Customized attributes can also be defined by the user. An alternative to show all the active attribute on an object is report attribute. For example, the miss outstanding reg has several attributes listed by this command. We can use getAttribute to specifically query one particular attribute, such as is hierarchical in this case. It returns false means the cell under query is not a hierarchical cell, but a leaf cell. Report cell is another commonly used command to report attributes, especially for cell objects. Personally, I would like to use connection and verbose switch along with it to show connectivity information on each pin of the cell. Topic 5. Basic tracing commands. Sometimes we would like to find out the immediate fan in or fan out of a cell. Here let's look at one example in the context of a timing report. On the left-hand side is a data path launch from if stage and capture at ICAKE missing outstanding reg. There is a cell cache memory /U5322 which has 4 fanouts. As shown on the right-hand side, these fanouts are cell U360, U361, U541, and U610. According to the definition of immediate fanout, they are all immediate fanout of cell U5322. Note that on the timing path, only path going through cell U361 is shown. Assuming we don't have the knowledge of what these 4 fanouts are, we can use all connected leaf command to find out a complete list of cells that is immediate fanout of the driver cell. If we apply all connected leaf on the driving net N323, it will return the driver pin U5322/Y and 4 sinks. U610/A1, U541/A1, U360/A and U361/A. Same holds true if we apply the command on the pin object. The command can return net N323 is the only net connected to pin 5322/Y. Finding the fan-out cone is also easy. Let's look at another cell ICAKE 0/U65 on the timing path. We can use all fanout flat from command on the output pin Y to list all cells that consists of its fanout cone. In this example, the results returned will be the pin Y itself and the input D pin of the miss outstanding reg. The level switch controlled how many layer of fanout cells it returns. A commonly used switching is endpoint only, which make the command only returns the endpoints pin object among all fanout cells. A minor tweak option with switch only cell will return the cell object instead of pin object. Very similarly, all fan-in flat to command can be used to trace back the fan-in cone of a particular cell or pin. It also comes with level switch, but what make it different is since the results are fan-in, we need to use start point only to find out the start point. Topic 6. STA objects. After talking so much, you may have noticed the cells or nets or pins are all treated as objects in the tool. If we store the output from getCell command into a variable and print it out into standard TCL, it returns something start with cell with a string of number. This is the pointer to the design object used inside the tool engine. We can use query objects command to translate it into human-friendly name. Or we can use getObjectName to return the human-friendly name as a command outputs. Another trick I would like to show is to split the command output into multiple lines. The default output of a command will be printing the design objects one followed by another in the same line. If there are too many of them, tool will display only up to a certain limit. You can try using this line or put it into a little TCL procedure to split the command output and print the instances one line for each. Another useful procedure to debug scripts issue is proc body. It will display the content of a procedure. If you are not sure where some procedure comes from and what it is doing, you can use this command to find out the source code of the procedure. Chapter Summary. In Chapter 1 we just went over the definition of static timing analysis, get to know the great power as well as the limitation of this methodology. We also have learned the first concept involved in STA, the operation condition, which is a fundamental precondition to watch before all subsequent analysis and checks. Later on, we know how the tool extend the analysis space by scaling libraries characterized at certain operation conditions in order to cover a large range of design possibilities. In the end, we revealed all the necessary inputs needed to conduct a STA run. On the side, we have learned some basic terminology and commands in STA design tools. We get the idea what is hierarchical cells or pins, fan-in and fan-out logic cone. Query commands like get cells or get pins, tracing commands like all connected, all fan-out. Keep on learning, you already had a good start.